We can solve x to the power k congruent to a mod n provided the greatest common divisor of k and phi of n is 1. But if n is greater than 2, phi of n will always have a factor of 2. That's because if n is greater than 2, it must have a factor that is a prime p, or a power of a prime p to the n. In either case, phi of n will have a factor of p minus 1, and if p is an odd prime, this means phi of n will have a factor of 2. Meanwhile, if p is an odd prime like 2, then n greater than 2 only occurs if we have a factor of the form 2 to the n, and again, phi of n will have a factor of 2. And so this approach never works on x squared congruent to a mod n. For this reason, quadratic congruences require a special study. Now, it's still true that a squared is equal to negative a squared, but if we're working mod n, we have negative a congruent to n minus a. Squaring both sides gives us, and this means that only half the numbers mod n can be perfect squares, or perhaps even less. So for example, we might try to find the perfect squares mod 7. So we note that 1, 2, and 3 squared are, and note that negative 1 is congruent to 7 minus 1. So negative 1 squared is congruent to 6 squared. In other words, 1 squared is congruent to 6 squared. Likewise, negative 2 is congruent to 7 minus 2, and so that means negative 2 squared is congruent to 5 squared. But negative 2 squared is also 2 squared, and so 2 squared and 5 squared are congruent. And likewise, 3 squared and 4 squared are congruent. So the squares of 4, 5, and 6 don't introduce any new values. Suppose x squared is congruent to a mod n. We say that a is a quadratic residue of n, but if no x exists where x squared is congruent to b mod n, then b is a quadratic non-residue of n. And it's worth remembering, nothing should be ignored. While x squared congruent to 0 always has a solution, we typically ignore it. Now, remember, we should begin our analysis with odd primes. So if n is an odd prime, some prime of the form 2k plus 1, then we might consider 1 squared, 2 squared, 3 squared, and so on. And since negative 1 is negative 1 plus the modulus, then negative 1 is congruent to 2k, and so negative 1 squared is congruent to 2k squared, but negative 1 squared is just 1 squared. So 1 squared and 2k squared are congruent. Likewise, negative 2 is congruent to negative 2 plus the modulus, and so that tells us that and so 2 squared is congruent to 2k minus 1 squared. And we can continue in this fashion all the way up until we get to negative k, which is congruent to k plus 1, and so negative k squared and k plus 1 squared are congruent, and that includes all possible values. So if n is an odd prime, then we have at most k quadratic residues, namely the squares of the values from 1 through k. Could we have less? Well, suppose again p is an odd prime 2k plus 1, and suppose that I squared is congruent to j squared, where both j and I are less than or equal to k. Then, because they're congruents, their difference is congruent to 0, and we can factor this as, so we know that p has to divide the product. But p is an odd prime, so we know that p has to divide one of the factors. Since I minus j is less than k, which is definitely less than p, p can't divide the difference. so that means P has to divide the sum. But the sum, because I and j are both less than k, is less than 2k, which is less than P, which means that P can't divide the sum either. And what this means is that if P is an odd prime, there are exactly k quadratic residues. And what's that flapping sound? Suppose A is a quadratic residue of P. Then we know that x squared congruent to A has a solution x equal to B, and we also know there's a second distinct solution, P minus B. Note that if B and P minus B are equal, then P has to be 2B, but remember we assume P to be an odd prime. So that means these k quadratic residues correspond to 2k distinct values mod P, but there are only 2k values mod P, 1 through 2k, and consequently, if A is a quadratic residue mod P, the equation x squared congruent to A mod P has exactly two solutions.